As a maintenance technician, a big part of your job is going to be replacing damaged gearbox components. To do this, you're going to need to know how a gearbox can be safely and properly taken apart and then reassembled. In this program, we'll look at the disassembly and reassembly of two types of gearboxes, a double reduction unit and a small worm gear unit. We'll look at the basic procedures necessary for taking these units apart, as well as learning about some of the measurements and adjustments that are typically made during the process. In this first part of the program, we're going to begin looking at the disassembly of a typical double reduction gear unit. We'll follow a maintenance technician as he begins an overhaul of the unit and takes some typical gear and shaft measurements. A couple of things to remember as you watch the procedure. First, keep in mind that although these gear units can weigh hundreds of pounds, the internal mechanisms are quite delicate. Whenever you're working inside one of these units, extreme care should be used. Secondly, it's essential that the work area be kept clean. For example, one thing you want to do is clean the outside of the gearbox casing before you start to take the unit apart. Dust, dirt, water, or other foreign materials that make their way into a gearbox can cause some serious damage. To begin the disassembly, the gearbox lubricant is drained. To do this, the upper vent plug and lower drain plug are removed. When the unit has been drained, a hammer and center punch are used to match mark the upper and lower halves of the gearbox. The match mark will make reassembly and adjustment of the components easier later on. The bearing end caps are marked in the same manner. Next, the drift pins or alignment pins are removed from the casing halves. As a general rule, drift pins or alignment pins are removed and replaced first during the disassembly and reassembly of the gearbox casing halves. Next, the bolts which connect the bearing end caps to the upper half of the housing are removed, marked or tagged to indicate their function, and then stored in a clean, secure container. All of the gearbox parts should be treated this way to ensure proper reassembly. The bolts which connect the bearing end caps to the lower half of the housing are then loosened, and the end caps are backed out slightly by hand. The technician then removes the housing bolts. At this point, the upper housing half can be lifted clear of the gearbox. The lift should be straight up, and the housing should be guided carefully to prevent it from coming into contact with any of the other gearbox components. When the housing is set down, it should be placed on a non-abrasive surface. An abrasive surface, such as concrete, could damage the seating surface of the housing seals. At this stage of the disassembly, the technician is able to make several types of checks or measurements. These checks and measurements are made to try and isolate possible problems within the gearbox. The four checks we'll be making here are for end play, backlash, shaft runout, and tooth contact. First, the amount of end play is measured. End play is the amount of axial movement of a shaft. In this case, the gear shafts. This measurement is important because too much end play can indicate a problem, such as a worn bearing or a bearing housing. There are a couple of different methods commonly used to check end play. The first one we'll see uses a pry bar to physically move the gear shafts inside the gearbox. Another method uses feeler gauges to measure end play. Now let's first look at the pry bar method. With this method, the lower bearing end cap bolts must first be torqued to their proper value. This ensures that the shaft is properly positioned and that the bearings in the shaft will not slide out the side of the gearbox. Then the shaft should be turned through a few rotations to make sure the bearings are properly lubricated. Next, a dial indicator is mounted so that it is perpendicular to the side of the gear. The dial indicator button should touch the side of the gear with the indicator's stem slightly depressed. A pry bar is then used to move the gear and shaft toward the dial indicator. A block of wood should be placed between the housing and the pry bar to prevent any damage to the housing. Continue to move the gear and shaft until they reach the limit of their axial movement. The dial indicator can then be zeroed as the gear and shaft are held in position. With the indicator zeroed, the pressure on the gear and shaft should be slowly released, and the pry bar and wood block should be moved to the other side of the gear. Then the gear and shaft should again be moved to the limit of their axial movement. The dial indicator reading now shows the total amount of end play for the shaft, which in this case is 2.5 thousandths of an inch. To double check the values you get, the end play measurement should be made again. When the readings are verified, the end play measurement should be done on the other shafts in the gearbox. All of the readings should be recorded and compared with company or manufacturer specifications, which in this case are between 2 and 3 thousandths. Any problems you find should be noted for possible adjustment later. Now, some gearboxes require a different method to check end play. For instance, some gearboxes may not have enough room in them to use a pry bar, or else the type of mount on the gear shaft may not allow the gear to be pried on. In these cases, the feeler gauge method is normally used to check end play. With this method, a feeler gauge is used to measure the gap between the bearing end cap and the bearing. This measurement is made on both ends of the gear's shaft. Then the two measurements are added together to get the total amount of end play associated with the shaft. A little later on in the program, we'll see how end play can be adjusted if it's not within specifications. Another measurement that may be taken is backlash. Backlash is the freedom of movement a gear has while its mating gear is held stationary. Excessive backlash could be an indication of worn parts. Backlash is measured by mounting a dial indicator so that its stem is perpendicular to the center of one of the gear's teeth. Then, while holding the mating gear stationary, the gear is rotated until the teeth of each gear contact each other. The dial indicator is then zeroed, and the gear is turned in the opposite direction until its teeth again contact the teeth of the mating gear. The dial indicator reading now shows the amount of backlash associated with the gear set, which in this case is 3 thousandths of an inch. As before, the backlash reading should be taken again to verify it and then recorded and compared with the specifications. Any problems or abnormal readings are noted. One way to check that the stationary gear doesn't move is to mount a second dial indicator perpendicular to the gear's teeth. The dial should be at 0 throughout the test. Any needle movement would indicate the stationary gear had moved. In addition to end play and backlash, a check for tooth contact may be made. Checking the tooth contact pattern is done to find any misalignment problems. The first step for this check is to clean the gears. Next, a thin coat of bluing is applied to the teeth of one of the gears in the mesh, usually the pinion. The gears are then rolled, and the bluing transfers to the mating gear at the contact points between the gear teeth. The transfer leaves an impression or pattern of how the gears contact each other as they roll through their mesh. The gear teeth should contact each other near the center of the teeth, and the line of contact should be straight across the face of the teeth. If the tooth contact pattern is not centered, or if it is unevenly distributed across the face of the gear teeth, it may be an indication of worn gears or bearings or of a misalignment problem in the gearbox. In addition to showing the gear teeth pattern, the bluing may also highlight other gear problems, such as scoring or pitting. Now, the last step we're going to look at here is taking a shaft runout measurement. Shaft runout uses a dial indicator to measure any distortions in the shaft. A bent or bowed shaft could cause any number of problems, such as causing bearings to wipe or gear teeth to wear or break. When the dial indicator is mounted, it is positioned perpendicular to the shaft's axis of rotation and as near as possible to the middle of the shaft. Occasionally, the gear arrangement may make getting at the middle of the shaft impossible, so the reading should be made as close to the middle as possible. The indicator should be zeroed, and then the shaft is rotated. Any distortions, like a bowed or warped shaft, will show up as needle movement on the dial indicator. If the shaft runout is outside of the manufacturer's tolerances, the shaft will have to be replaced. Well, at this point, we've seen how the upper half of the gearbox housing is removed, and we've run through some of the measurements that are typically taken at this point in the disassembly. Take a few minutes now to read over this material in your textbook and answer the questions. When we return, we'll complete the disassembly and continue with the overhaul. In the first part of the program, we began disassembling a typical double reduction gearbox, and we saw some of the measurements that can be made in the process. In this part of the program, we'll complete the disassembly and look at a few additional checks. We'll also take a look at one method of removing a gear from a shaft. As you recall, we had just completed a runout reading to check for any shaft distortion. The next step is removing the bearing end caps. To do this, the remaining end cap bolts are removed and the end caps are slid out of the bearing housings. In some cases, as you remove the bearing end caps, you may find a shim or group of shims between the end cap and the housing. The shims help to position the bearings, shafts, and gears inside the gearbox. As the shims come off, they should be marked to indicate which end cap they go with. This will make the reassembly and adjustment of the gearbox easier. End caps which have shafts passing through them, like these, also have oil seals that prevent oil from leaking out of the gearbox along the shafts. These seals must be protected as the end caps are slid off. One way to do this is to wrap paper or plastic sheeting around the shaft, and then slide the end cap and seal off over the wrapping. This helps protect the seals from being damaged by any irregularities along the shaft, such as keyways or shoulders. Now, the type of bearing end caps that we've looked at so far only position the shafts inside the gearboxes. The weight of the bearings, shafts, and gears are taken up by the bearing housings. In some cases, bearing end caps may also support the weight of the bearings and associated gears and shafts. As you can see in this illustration, if this type of end cap is removed before the bearing and gear weight is taken up, the bearings, shaft, and gears may drop inside the gearbox and damage other gearbox components. To remove this type of end cap, take out the bolts connecting the end cap to the upper housing. Then loosen the lower housing bolts and back out the end caps to clear the upper housing. Next, remove the upper housing and support the shaft weight with a sling. Finally, remove the rest of the bolts and the end cap. As before, if the end cap has a shaft passing through it, its oil seals must also be protected. Now let's go back to the demonstration and see how the gears and shafts can be taken out of the gearbox. To lift the shafts, a sling should be used. As the lift is begun, the mating gear should be rolled to disengage the mesh. The direction of the lift should be straight up, and the shaft should be guided to avoid damaging other components in the gearbox. When the gear and shaft are set down, the shaft should be placed on supports so that the weight of the assembly doesn't rest on the gear teeth. The remaining gears and shafts are then removed in the same way. Now that the gearbox is completely disassembled, let's take a look at another of the measurements that can be made on the unit: the bearing housing's inside diameter. To take the diameter measurement, the housing halves first have to be put back together. And let's see how this is done. First, the seal areas on the upper and lower halves of the housing should be inspected. This ensures that the seal areas are clean and free of any imperfections that could prevent a proper seal. Next, the manufacturer's specification for the gearbox should be checked to see if the housing gasket must be in place before the measurement is taken. In this case, the gasket isn't needed. If a gasket is required and is either not installed, or if the wrong size is installed, the measurements will be wrong. First, the upper half of the housing is reinstalled. Then the drift pins are installed. This will draw the upper and lower housings into alignment and make it easier to install the housing bolts. The housing bolts must be torqued to their proper value in the proper sequence, or the diameter measurement will be wrong. For this particular gearbox, this is the order in which the bolts should be torqued. Torquing in the right order ensures that the housing halves are not pulled out of alignment. Once the housings are together, the diameter measurement can be made. Using an inside micrometer, the technician checks the inside diameter of the bearing housing. This measurement should be taken diagonally across the bearing housing. A second measurement is then taken approximately 90 degrees from the first. A measurement should not be taken between these 2 points. Imperfections in the seal could cause an error in the reading. Record your measurements and then check them against the manufacturer's technical information to see if they're within the specifications. If they aren't, there are a couple of things you should check to make sure that your measurement was made accurately. First, recheck the housing alignment. Even a small misalignment between the upper and lower housings can throw off the diameter measurements. You may also want to recheck the torque and torque pattern on the housing bolts. Using an improper torque pattern or the wrong amount of torque can also throw your measurements off. Finally, recheck the seal areas to make sure they're clean. If all of these items check out okay, then your measurement was probably accurate and the bearing housing will have to be repaired. Now, with the bearing housing measurements taken, we're ready to clean and make a visual inspection of the disassembled gearbox and its components. A visual inspection may turn up a problem with the unit that the measurements we took earlier did not indicate. You should begin the inspection by taking a close look at all of the gears. Look for any unusual wear, scoring, pitting, and chipped or broken teeth. Next, inspect the oil seals in the bearing end caps for nicks or cracks that could cause the seals to leak when the gearbox is back in operation. The oil troughs in the lower housing should also be checked to make sure they're clean, tightly secured, and undamaged. A loose trough, or one that has been damaged, like this one, will leak and can prevent proper bearing lubrication. A dirty trough could pass debris to the bearings. Either of these conditions could damage the bearings. The oil sump should also be checked to see that it's clean as well. If you find metal particles or shavings in the sump, it could be an indication that the gears, bearings, or other components have worn. Both the oil troughs and the oil sump should be wiped clean, along with the seal areas, the gears, and the shafting. And finally, check the bearings for evidence of wear or damage. Any worn bearings should be replaced. Now that we've seen some of the checks and readings that are made on a disassembled gearbox, let's look at a common maintenance task: the removal of a gear from a shaft. A gear may have to be removed from a shaft and replaced for several reasons, including worn or broken teeth, severe pitting, and scoring. To demonstrate one of the ways in which a gear may be removed from a shaft, we've taken a gear and shaft from another gearbox and mounted the assembly to make the removal easier. On this type, a snap ring must be taken off using snap ring pliers. Now a gear puller is used to remove the gear from the shaft. Make sure to use a soft center between the gear puller and the end of the shaft to prevent any damage to the shaft. After the gear is taken off, the gear key can be removed by hand from the keyway. To reinstall the gear on the shaft, it is first placed on the bed of a press. The shaft with the gear key is then installed and lined up with the gear. A soft center is placed between the press and the end of the shaft. Then the press is operated and the gear is pressed onto the shaft. The gear and shaft assembly is then removed from the press and the snap ring is installed as before. Remember, like many pieces of equipment, improper press operation can damage gear shafts or cause personal injury. So be sure to check the press operating manual for the correct procedures and precautions. Now keep in mind that the procedures we've just seen for reinstalling a gear on a shaft can vary. For example, a gear may also be heated and then slid onto a shaft. Also, be aware that gears like these are generally replaced in sets. So the procedures we've just seen would be repeated for each gear and shaft assembly. You'll find more information in your textbook about replacing gears. Well, in these first two parts of the program, we've seen procedures commonly used for taking apart and inspecting a double reduction gearbox. Although the steps you've seen are typical, there may be additional procedures or inspections that your company requires you to do. Now, when we come back, we'll see how the double reduction unit can be reassembled. Reassembling a gearbox is very much like the disassembly, but done in reverse. In this part of the program, we'll see how a double reduction gearbox is reassembled. Then we'll take a look at a few more of the checks and measurements that are carried out as the job nears completion. Although the steps you'll be seeing are typical, your plant may require some additional procedures or inspections. So be sure you're familiar with the proper procedures and equipment you'll be using on the job. Now, before we get started, a reminder again about the importance of maintaining a clean work area. Even a small piece of debris, such as a metal shaving, can have disastrous effects if it finds its way into a gearbox. A metal shaving in the oil sump, for example, may be carried into the gear mesh by the oil flow. Once in the mesh, the shaving could severely damage the gears. The shaving could also be carried into one of the bearings, which could damage the bearing almost immediately. So it's very important to keep the gearbox and its components free of dirt and debris. In short, you should make sure that nothing gets into a gearbox that doesn't belong there. The first step in the reassembly is to reinstall the gears and gear shafts. The first shaft to be reinstalled is carefully lowered back into position in the gearbox. Be sure not to nick or bump the gears as each gear shaft is lowered. Even the slightest nick on a gear tooth can cause problems. As each of the other gear and shaft arrangements is lowered into the gearbox, its mating gear and shaft should be slowly rotated to engage the gear mesh. With the shafts installed in the gearbox, the next step in the reassembly is installing the bearing end caps. The technician first places the shim pack and gaskets in position on the end cap. He then inserts the end cap into the lower half of the gearbox housing and installs and torques the lower end cap bolts. Remember, if the end cap has an oil seal, you have to be careful not to damage it. As we saw earlier, you can wrap plastic sheeting or construction paper around the shaft and then slide the end cap on over the protective wrapping and then into the lower half of the gearbox housing. Now, a few words at this point about the end cap gasket. If the wrong sized gasket is used, it'll be very difficult, if not impossible, to adjust the end play on the associated shaft. Also, some gearboxes don't use gaskets, and in some cases, a gearbox may have shims which act as gaskets. So make sure to check the manufacturer's technical information for your gearbox. Earlier, we looked at an end cap that supports the weight of its associated shaft and bearings. The steps for reinstalling these shafts are basically the reverse of the steps used to disassemble them. We can use a simplified illustration to get a better idea of how this is done. First, the shaft is carefully lowered into the gearbox. The weight of the shaft remains supported until the bearing end caps are installed. Shim packs and gaskets should be installed along with the end caps. The lower end cap bolts are then installed and torqued into place. With the right gaskets installed and the bearing end caps in place, you can begin making some checks and measurements. We'll be looking at two checks on this unit: end play and tooth contact. First, let's see how the amount of end play can be measured. As you recall, end play is measured by positioning a dial indicator perpendicular to a gear side, moving the gear and shaft in one direction, zeroing the dial indicator, and then moving the gear and shaft in the opposite direction. At this point, the dial indicator is reading the total amount of end play on the shaft. End play on a shaft is adjusted by adding or removing shims from between the end caps and the housing. The total amount of shims added or removed is divided by 2, and the resulting number is applied to both ends of the shaft to prevent misalignment. For this gearbox, end play is increased by adding shims and decreased by removing shims. On some gearboxes, the shims are located between the bearing end caps and the bearing. With this type of gearbox, removing shims will increase end play and adding shims will decrease end play. Each time that shims are either added or removed, the end play measurement is retaken. Also, because it's possible that each shaft in a gearbox may have a different amount of required end play, each shaft should be checked and adjusted to the correct end play value. For example, on this shaft, the end play should be adjusted to between 1 and 2 thousandths of an inch. The end play on this shaft should be between 2 and 3 thousandths of an inch. It's very important that the shafts have just the right amount of end play. If there's too much end play, the gears may not mesh properly, which could cause rapid wear or gear failure. If there's too little end play, the bearings may be constantly overloaded, which could lead to rapid bearing failure. The proper tolerances for end play can generally be found in the manufacturer's technical information. The other check we'll make here is of the tooth contact pattern. Now, this is done by applying bluing to one of the gears in the mesh, usually to the pinion, as you see here, and then rolling the gears through their mesh. Since we're reassembling the gearbox with new parts, we wouldn't expect to find a problem with the tooth contact. However, the check is still performed to make sure the gears are contacting each other as they should be. If they aren't, then it means a problem went unnoticed earlier in the procedure or that one of the new parts is bad. Well, at this point, we've completed most of the reassembly, and we've performed the end play and tooth contact checks. When we return, we'll complete the reassembly and look at the remaining measurements that are generally made. In the last part of the program, we began reassembly of the double reduction gearbox. And we saw a couple of checks that are typically made during the reassembly process. In this part of the program, we'll see the technician check backlash and then complete the reassembly. We'll also take a look at bevel gears and at some of the adjustments that can be made on them. Let's begin with the check of backlash. You'll recall that backlash is measured by mounting a dial indicator so that it's perpendicular to the center of one of the gear's teeth. While holding its mating gear stationary, the gear is rotated until the teeth of the two gears contact each other. The dial indicator is then zeroed, and the gear is turned in the opposite direction until its teeth again contact the teeth of the mating gear. The dial indicator reading shows the amount of backlash associated with the gear set. As before, the reading is recorded and then compared with specifications. With most gearboxes that contain spur gears or helical gears like the one we're using here, Backlash and tooth contact can't usually be adjusted. In most cases, though, in gear units repaired with new gears, the things that these two tests check for, gear wear or misalignment, aren't generally a concern. The checks are made anyway, however, to be sure that everything is within specifications. Now, with all of the gearbox checks completed, we're ready to finish the reassembly. How a gearbox is finally assembled will depend on how it's going to be used. Generally, a gearbox will either be returned to service or placed in storage as a ready spare. If the unit is to be placed in storage, several preparations are generally done. First, a thin coat of lubricant, such as grease or gear oil, is applied to the gears, shafts, and bearings. The lubricant is to protect the gearbox against corrosion while it's in storage. Next, the end cap bolts are loosened, and the end caps are backed out slightly. This is to allow room for the upper housing to be replaced. Then the oil sump and housing seal areas should be checked to make sure they're free of debris. It's important that both the upper and lower housing seal areas be checked. Any contaminants could cause an improper seal that could lead to leaks later on. Next, the upper housing can be lowered back into place. The housing should be lowered straight down onto the gearbox and should be guided to avoid damage to other gearbox components. Then the drift pins are installed. This will draw the upper and lower housings into alignment and make it easier to install the housing bolts. Then the housing bolts should be installed and torqued to the proper value. You can check the manufacturer's technical information for the proper amount of torque and torque pattern. Applying the wrong torque can throw the gears and shafts out of alignment and lead to oil leaks. Next, the upper bearing end cap bolts should be installed, and then all of the end cap bolts should be torqued to their proper values. Now that the unit is reassembled, a thin coat of lubricant is applied to the exposed areas of the shafts. This protects the shafts against corrosion while in storage. And finally, a protective wrapping is placed around the shafts to guard against damage during the move to the storage area. The gearbox is now ready to be placed in storage. If the gearbox is going to be put back into service, most of the final assembly steps will be the same. The difference is in how and when the unit is lubricated. In some cases, a gearbox may be filled with lubricant before it is moved to its service location. Doing this, however, may make the gearbox harder to control when it's lifted because of the movement of the oil inside. This is a bigger concern with larger gearboxes, but in all cases, you should check your company's procedures to make sure the oil is added at the proper time. Earlier, we said that backlash and tooth contact usually couldn't be adjusted on a gearbox which used helical or spur gears. However, on a gearbox which uses bevel gears, they can be adjusted. As you'll recall, a bevel gear is conical in shape and is used to transmit power between intersecting shafts, usually set at 90-degree angles. Other shaft angles may be used, but 90 degrees is the most common. As you can see from this illustration, the bevel gear is mounted on a shaft which is supported by bearings on both ends. The bevel pinion is normally mounted on a shaft extension, with a bearing mounted here. Because of the way the gears are mounted, the bevel gear can be moved up or down and the pinion can be moved back and forth. This movement allows the gear and pinion to be spaced closer together or farther apart. And because these spacing adjustments can be made, backlash and tooth contact can be adjusted. However, because each of these adjustments will affect the other, the corrections have to be made in steps and continually checked to see that all the values are kept within specifications. Now, let's see what we mean by taking a look at how backlash can be adjusted. Backlash adjustments are made by moving the bevel gear and its shaft up or down. If there's too little backlash, the gear is too close to the pinion and must be moved farther away. In this case, the gear is moved by removing shims from above the upper bearing and placing them under the lower bearing. This adjustment increases the backlash. If there's too much backlash, the gear is too far away from the pinion and must be moved closer. This is done by taking shims from under the lower bearing and placing them above the upper bearing. This adjustment will decrease the amount of backlash. With both of these adjustments, the total number of shims remained the same, so the end play of the gear shaft was unaffected. However, in both cases, tooth contact was affected, so corrections will have to be made. If the tooth contact check results in a narrow band of bluing that is high on the teeth, then the pinion is too far out and must be moved closer in. If the tooth contact check shows a band of bluing that is low on the teeth, then the pinion is too close and must be moved farther out. The pinion can be moved in or out by adding or removing shims here. Making this adjustment, though, affects the backlash of the gear mesh. So with bevel gears, an adjustment for tooth contact can affect backlash. Repeated adjustments may be required until the gear and pinion are set properly for both tooth contact and backlash. In this part of the program, we've completed the reassembly of a double reduction gear unit, looked briefly at a backlash measurement, and seen how a gearbox is prepared to be put either back into service or into storage as a ready spare. And finally, we looked at bevel gears and saw how they could be adjusted for backlash and tooth contact. When we come back, we'll begin taking a look at another type of gearbox, one that uses worm gears. Up to this point, we've seen how a typical double reduction gearbox can be taken apart and reassembled. And we've looked at some of the checks that can be made during the process. Now, in some cases, other equipment, such as a clutch or a motor, may be part of a gearbox. These components must be handled properly in order to repair or replace the unit's gearing. For the rest of the program, we're going to look at a worm gearbox that contains other components. First, we'll look at some of these components and then see how the unit can be taken apart. We'll see how to replace some of the gearing, and finally, how to reassemble the gearbox. The type of unit we'll be working on is called a motor operator. It's used to position valves electrically using gearing. Motor operators are available in several different types of gear arrangements, but the most common ones use worm gears. The main reason for this arrangement's popularity is that it offers relatively high reduction and torque ratios in a small gearbox, as compared to other types of gear arrangements. This is a typical worm gear operator. It consists of a motor, a clutch operating lever, a hand wheel, a bearing cartridge, a gearbox, and a switch compartment. We've removed the switch compartment cover so that we can get a better look at a couple of additional components, a limit switch and a torque switch. A limit switch limits the valve stem travel, and a torque switch limits the torque that's applied to the valve stem. Each of these switches accomplishes its function by turning off the motor operator. The components in the gearbox are arranged basically in three groups: the drive sleeve components, the worm shaft components, and the clutch operating components. Let's look at the drive sleeve components first. The drive sleeve contains a bevel gear that engages the limit switch and operates it, the worm gear, and part of the clutch, including the clutch gear, spring, and key. Basically, the clutch allows either the worm gear or the hand wheel to turn the drive sleeve. The drive sleeve transmits this motion to the valve stem. The next set of components we'll look at is the worm shaft components. The worm gear is driven by the worm, which is mounted on the worm shaft. Other components on the worm shaft include a helical gear, which is driven by a gear on the motor shaft, a cam, and a spring assembly which positions the worm in the gearbox. Other parts include a declutching fork, which positions the clutch on the drive sleeve, a lever, which is moved to switch the motor operator into manual or hand wheel operation, and a declutching mechanism. The declutching mechanism locks the operator in manual. The mechanism is unlocked by the cam when the motor starts. This allows the operator to automatically shift to motor drive when the motor starts. Now that we've seen some of the operator components, let's see how the unit can be taken apart. We're taking the operator apart to replace the worm and worm gear. The unit has already been partially disassembled. It's been removed from its valve stem, and the grease has been removed by flushing the unit with an approved solvent. The first step in the disassembly is to remove the limit switch. After this is done, the exposed pinion should be visually inspected to see that it's not damaged. Any problems should be noted. We'll be looking at the gearing associated with this pinion a bit later in the program. As we've seen before, as each part of the gearbox is disassembled, it should be marked to identify it and then set carefully aside. Next, the torque switch is removed. This is done by disconnecting the torque switch bolts and then removing the unit. Next, the motor can be removed. To do this, the motor leads are disconnected in the switch compartment and the bolts holding the motor are removed. Then the motor leads are fed through the conduit and the motor is removed. With the motor removed, the helical pinion is exposed at the end of the motor shaft. The pinion should be inspected for any signs of obvious damage. You should also inspect the helical gear on the end of the worm shaft. Any problems should be noted. At this point, this unit is placed into manual so that it can be taken further apart. This is done by depressing the clutch operating lever, which can then be removed. Placing the unit in manual releases the clutch key from the worm gear and allows the worm to be easily withdrawn from the gearbox. Next, the bearing cartridge is removed. The bearing cartridge supports one end of the worm shaft and is removed by taking out the screws that hold it to the gearbox. Now the worm and spring assembly are removed. The spring assembly is pulled out by hand along with the worm, leaving the worm shaft in the gearbox. The spring assembly positions the worm inside the gearbox. The amount of spring pressure provided by this assembly is factory set using this lock nut. Now, since we're removing and replacing the worm and worm gear, there's no reason to disassemble the spring assembly. But if you ever have to disassemble this type of assembly, you must do it properly, or you won't be able to get the spring pressure set correctly when you reassemble it. For this type of spring assembly, the lock nut must be removed. As this is done, the number of turns necessary to remove it must be counted. The lock nut must be screwed back on with the same number of turns when the unit is reassembled to ensure the proper spring pressure. Next, the declutching mechanism is taken out. This is done by loosening the screw on the top of the declutching mechanism and then sliding the mechanism off its shaft. Next, the worm gear can be removed. To do this, the unit's drive sleeve must be taken out. Removing the sleeve is a two-step process. First, the upper housing cap bolts are removed, and the upper housing cap and hand wheel assembly are pulled off. Then the drive sleeve assembly is pulled straight up out of the gearbox. Mounted on the drive sleeve is the bevel gear that drives the limit switch. This gear should be inspected for signs of damage. After the drive sleeve lower bearing has been removed, slide off the lower drive sleeve spacer and then the limit switch bevel gear. This bevel gear is keyed on the drive sleeve. Its key should be removed and then set carefully aside. Then the worm gear can be slid off the end of the drive sleeve. The next step is to remove the worm from the spring assembly. This worm is removed by taking off an internal retaining ring. Generally, snap ring pliers are used for this. The worm can then be slid off of the spring assembly. In this part of the program, we've taken a brief look at what a motor operator is. We've looked at a typical worm gear operator's internal components. Then we saw how one type of worm gear operator could be disassembled. When we come back, we'll talk a little more about worm gears, and then we'll see how the worm gearbox we've just seen can be put together again. Earlier in the program, we were looking at a double reduction gearbox unit and at some of the checks and measurements that are taken while the unit's being worked on. Well, just like the double reduction unit, there are several checks and measurements that are commonly performed on worm gear units. For the rest of the program, we're going to take a look at some of these checks and talk about some of the characteristics of worm gears and how they're aligned. First, though, let's begin by reassembling the worm gear unit. The steps are basically the reverse of the disassembly procedure. The first step is to install a new worm gear on the drive sleeve. The drive sleeve is lubricated with a thin coat of grease, and then the new gear is slid over the sleeve. Next, the bevel gear key is installed in the drive sleeve, and the bevel gear for the limit switch is slid into position over the key. Then the lower drive sleeve spacer is reinstalled. After the lower drive sleeve bearing is pressed onto the drive sleeve, make sure that the bearing is pushed up against the drive sleeve shoulder, or the axial position of the worm gear will be incorrect. Now, the drive sleeve assembly and the upper housing cap and hand wheel assembly can be reinstalled. Part of this step is placing a gasket under the housing cap. It's important that the correct sized gasket be used. A wrong-sized gasket can throw off the worm gear's position. Many manufacturers will specify the correct gasket size to be used. The manufacturer of this unit recommends some specific steps to ensure that the right gasket is used. First, the upper housing cap and the housing surface seals must be cleaned. Then the drive sleeve is installed, and the upper housing cap is put in place without a gasket. Next, the distance between the upper housing cap and the main housing is measured. 10% should be added to this measurement, and then the closest gasket thickness or combinations that are available should be used. We can now install the new worm on the spring assembly. To do this, slide the worm onto the assembly and reinstall the internal retaining ring, making sure that the ring snaps into place. The next step is to reinstall the declutching mechanism. This is done by sliding the mechanism onto its shaft and then tightening the screw on top of the mechanism. Now, let's take a look at one of the checks that can be made on this motor operator. You'll recall that one of the checks we made with the helical gear unit was tooth contact. The tooth contact pattern had to be near the center of the teeth and straight across the face of the teeth. Well, with worm gears, the tooth contact pattern is a little different. This is an illustration of a single enveloping gear set. For this example, the worm rotation is clockwise. The point at which the worm thread enters the gear during rotation is called the entering side. Where the worm thread leaves the gear is called the exiting side. When a tooth contact check is done on a new set of worm gears, the pattern will appear here on the exiting side. After a few hours of operation, the contact pattern would appear like this. As you can see, the pattern area has expanded or spread out on the exiting side. After many hours of operation, the pattern has spread completely across the gear face. This change in the tooth pattern is due to the materials that the two gears are made from. The worm is often made of a metal such as hardened steel, while the gear is often made of a softer material such as bronze. As the two gears rotate, the worm gear wears slightly, and the contact between the two gears increases. This is normal for worm gear sets and compensates for small amounts of misalignment of the worm. However, if the initial tooth contact pattern appears on the entering side instead of the exiting side, a larger misalignment problem may exist, and this problem can be serious. Worm gear sets are generally very sensitive to misalignment. They must be mounted on shafts that are very close to being correctly aligned and at the right distance apart. The axial position of the worm is not as critical, but the worm gear must be in the right axial position so that it can wrap around the worm correctly. Even a small amount of axial misalignment of the gear can result in immediate gear set failure under load. Now that we've seen some of the patterns you might expect to find with a tooth contact check, let's reinstall the worm and spring assembly and actually make a tooth contact check. First, apply bluing to the worm and install it by sliding it over the splines on the worm shaft. Next, the bearing cartridge is installed over the spring assembly. A gasket is installed between the cartridge and the gearbox housing. Again, if the wrong thickness of gasket is used, the position of the worm will be incorrect. Now, turn the motor gear on the end of the worm shaft through several revolutions. This will transfer the bluing from the worm to the worm gear. Make sure that the motor gear is turned in the right direction. If it's not, the bluing won't transfer. Remove the worm and the drive sleeve from the gearbox and inspect the tooth contact pattern. The pattern should appear as a small area of contact on the exiting side of the worm gear. If it doesn't, then the alignment of the gear set is wrong. The most likely problem is that the axial position of the worm gear is incorrect. In this case, that would mean going back and checking the gasket size on the housing cap. If the contact pattern is correct, then the drive sleeve and the worm can be reinstalled in the gearbox. When the components have been reinstalled, the gearbox reassembly can be completed. The clutch operating lever is first reinstalled onto the end of its shaft and the bolt is tightened down. The unit should then be manually declutched by pressing down the lever. To test the declutching mechanism, reach into the unit and turn the motor gear on the end of the worm shaft. If the unit has been properly reassembled, the clutch operating lever should pop up and the parts should turn easily. If they don't, a problem exists in the gearbox and it'll have to be disassembled and checked out again. Finally, the motor and the torque and limit switches are reinstalled and the assembly is complete. So as you can see, the reassembly procedure for this type of unit is pretty much the reverse of what we did in the disassembly. And as we've seen with both the double reduction unit and the worm gear unit, there are several checks and measurements that go along with taking the units apart and putting them back together again. Well, in this program, we've looked at several different aspects of gears and gear equipment. In particular, we looked at two common types of gearboxes and saw how each could be disassembled and reassembled again. And in the process, we also took a look at some of the measurements and checks, like backlash and tooth contact, that are generally done while a unit is being repaired. Regardless of what type of gearbox you'll be working on, it's important that you have a firm grasp of the points that we've covered here. A knowledge of proper assembly and disassembly procedures is essential for correct gearbox maintenance. Take a few minutes now to review the material we've gone over here, and if you have any questions, be sure to clear them up with your instructor.